In this last section of Chapter 5, we're going to talk about something called differential equations. Differential equations are equations where either the way they were discovered or the fact that, or just your ability to write them requires you to use three different variables. Differential equations are always written in terms of y, x, and the derivative of y. So for example, this would be a differential equation. Y prime is equal to 2x minus xy. Notice there's three different things in here: x, y, and the derivative of y. Now with differential equations, we're always assuming that y is a function of x, okay? And that y prime, when I use that term y prime, it's the derivative of y in terms of x. So those are some things that we assume about whenever we're working with differential equations. So once again, the reason why it might be in this form is just because of how complicated the equation is, or if they discovered this equation from a specific relationship it had with its rate, which we've talked about that a little bit when we first talked about exponential equations, right? We'll look at an example of like that. So how do we solve something like that? Well, this is where integration comes in. Integration can help us solve these more complicated types of equations called differential equations. And we're going to use a specific strategy called separation of parts. Separation of parts follows 5 steps. And as I talk about these steps, I'll walk through it with my example equation up here. So my first step is I want to convert it to a differential equation. Okay? We've talked about differentials before. All a differential is instead of writing y prime, I'm going to write it dy over dx. And then if you remember, a differential is just getting dy on one side, dx on the other side. So I'm just going to multiply both sides by dx. And I'm left with dy equals 2x minus xy times dx. So there, step 1, done. I've got it as a differential. And this is where step 2 is where the name of this process comes from. I'm going to perform operations to separate. When I say operations, think like multiplication, division, addition, subtraction, whatever you need to do. Perform operations to separate the variables. What do I mean by that? Notice I've got dy on the left side of my equal sign and dx on the right side of my equal sign. Well, because of that, what I want is I want all of my y variable stuff on the left. Anything that deals with y, I want on the left, and anything that deals with x, I want on the right. So, with my example function, I want to get my y value over to the left side. But if I have xy right next to each other, how do I do that? Well, I can actually factor out an x. Both of these terms have an x in it, so I can factor out an x. And what do I get? I get dy is equal to 2 minus y times x times dx. Well, now I have 2 different terms, one that's completely in terms of y, one that's completely in terms of x, which means I can go ahead and divide by my term that just has y in it. And I'm left with dy over 2 minus y equals x dx. Perfect. I've separated my variables. All of my x stuff is on the right. All of my y stuff is on the left. That leads us into step 3. And this is where we integrate. This is where integration ends up helping us. Now, I will integrate both sides. Take a look at what happens when I do that. Let's start on the right side because that's the more simple one to look at. If I put that integration symbol there, I already have the dx part of my notation, which means I'm ready to go. I'm ready to integrate this. And that's a relatively simple antiderivative that I know how to find. I get x squared over 2 plus c. But if I integrate one side, I have to integrate the other side. But notice once again, it's all in terms of y. So it's a straightforward integral. Relatively straightforward integral. This is complicated enough. I do need to use integration by substitution here. I'm going to go ahead and call my denominator u, right? If I'm using substitution, I have to know what du is equal to. When I take the derivative of 2 minus y, I just get negative 1 dy. Solve for dy, I get negative du. What does this leave me with? This leaves me with the integral of 1 over u times negative du. I can bring that negative outside. Okay, so I don't need to put it there. I can just put it out here. And that is an integral I know how to take. What's the integral of 1 over u? That's just the natural log. Okay, so I get negative natural log. And remember, whenever I integrate, I have to put this absolute value with my natural log. Okay, now I didn't mention this earlier. I did put a plus c, right, after my x squared over 2 because I'm taking an indefinite integral. You should always have a plus c. Do I need to do that on the left side as well? Well, I could. You know, it's always a good idea because I took an antiderivative of the left side as well. But if I have an arbitrary constant on the left side and an arbitrary constant on the right side, I can combine those together just by subtracting. And if you combine two arbitrary constants, what do you get? Another arbitrary constant. So it turns out I only need one of these plus c's. So I always just worry about the plus c on the x side, and I don't worry about it on the y side. Okay. But you only need one. Okay. What do I do next? Well, I'm actually going to skip a step, and I'll talk about this later. But my final step, step 5, is, if possible, solve for y. Because that's the whole point of this, right? The whole point of what we're doing here is hopefully we can get y by itself. We can know what y is in terms of x. Well, this one takes a little bit of tricky manipulation here just at the beginning. I don't like the absolute value. It makes it hard for me to solve for y because the absolute value makes it a piecewise function. So what we're going to do is we're going to make an assumption here. We're going to assume that y is greater than 2. Okay? As long as y is greater than 2, then 2 minus y is going to end up being always negative. It's always going to be negative, right? If I plug in 3, I get 2 minus 3, which is negative 1. If I plug in 5, I get 2 minus 5 is negative 3, which is negative. So it's always negative. What is the absolute value going to do that? It's going to turn it positive. So what this allows me to do by assuming that is it allows me to take away the absolute value and just switch the order. Why am I switching the order? Because once again, the absolute value is going to change it to a positive version of the same number. Now, if I plug in anything greater than 2, I get a positive number, which is what we want. That's going to make this process a little bit simpler. I can go ahead and move this negative over to the other side just by multiplying everything by a negative 1. Okay, and I get natural log of y minus 2 equals negative x squared over 2. And sure, I could write minus c, but remember, c is just an arbitrary constant. It doesn't matter whether it's positive or negative. Okay, so I can just keep it as a plus c. Okay, how do I get rid of natural log? I raise everything to the e power. Okay, though the e and the natural log cancel out, and I'm just left with y minus 2 equals e to the negative x squared over 2 plus c. Now I can use some exponential properties here. Stay with me. I can use some exponential properties to do e to the negative x squared over 2 times e to the c power. And because, once again, because c is an arbitrary constant, e to the c power is also just an arbitrary constant. And so I can rewrite this as y equals c times e to the negative x squared over 2 plus 2. Once again, where I got this c from is just the fact that e to the c, since c is arbitrary, e to the c is also just some arbitrary constant. And I can rewrite it like that. Awesome. So what was the step that I skipped? Well, this step that I skipped didn't apply to what I gave you because it deals with if you have an initial value. So step 4, when given an initial value, solve for C. We saw some questions like this back in when we first learned about antiderivatives and indefinite integrals, right? Sometimes if they give you an actual data point, you can solve for what C is. I didn't give you a data point, and that's why we skipped that. But let's go back and say that I actually did. Let's say I knew that y of 0 is equal to 9. Remember, we're assuming that y is a function of x. So what is 0? 0 is an x value, and 9 is my corresponding y value. Well, that gives me two different numbers I can plug in order to solve for C. But where do I plug them in? I could go ahead and just plug them in all the way down here at the bottom, my finished product. But sometimes it'll be easier to plug them in right here, right after I'm done integrating, right? Because that's when the C first shows up. So the C will first show up when I finish integrating. And a lot of times it's easier to just go ahead and plug in your values here and solve for C. And that's why this is step 4 and not the final step. Let's try it. Let's try it from right here. Okay. Notice, remember my assumption that y was greater than 2. Is y greater than 2? Yep. So we're good to go. Okay. I get the natural log of 2 minus 9 equals, and then plugging 0 in for x. Okay. What do I get? I get negative natural log of negative 7, but what does the absolute value do? The absolute value makes that a positive 7 equals 0 squared over 2 is just 0, so I get C. Aha, it turns out C is negative natural log of 7. Now, we have to be careful because we did change C over the course of this, over the course of my simplifying process. So as I simplified, my C changed. For example, I multiplied by negative, so that C went from being a positive to a negative, but because it was arbitrary, I could just keep it as a plus C. And same thing down here. Here I did e to the C power, but because it was arbitrary, I just left it as a C. Well, that will get you into trouble if you solve for C up here, but you've already done all this work. So when you're solving for C, you have to pick and choose, or you have to decide one way or the other. You can't try and do both, because right now we're going to get into trouble because we did them both ways. So either when you first find your integral, solve for C there before you finish solving for y. Okay, so that's one option, is solve for C right then. Don't solve for y until you solve for C. Or your other option is go into solve for y and plug in your initial value down here. Because if you did what we did, I'd solve for C and I might think, oh, yeah, I can go ahead and plug that in for C right here. But it doesn't work because we did so much to C throughout my solving process. So I have to choose one or the other. So because I already solved for y, let's scrap what we did there and plug my initial value in down here. What did we say my initial value was? Y of 0 was equal to 9. So I'll plug in 9 for y and 0 for x. Okay. I'll subtract 2 on each side. I get 7 equals C times e to the 0. What is e to the 0? E to the 0 is just 1. So what is C equal to? 7. This gives me my final answer of y is equal to 7 e to the negative x squared over 2 plus 2. That's my function. Take a look at this one. Y prime is equal to 7 over x minus 3x squared plus x to the 6th. This counts as a differential equation, because it's in terms of x and y prime. It doesn't actually include a y at all, which is interesting. But if we think about using this same process, so my 5 separation of by parts steps. Here, let me put a square around this to make it a little bit cleaner. Well, a very bendy square. Okay. First, I want to convert to a differential. All that means is dy on the left side and dx on the right side. There's my differential. Step 2. Perform operations to separate variables. Well, what do you notice? This function's already separated. It's because it's only in terms of x. There's no y value I need to worry about getting over to the right side. So I'm ready. I'm ready to go ahead and move on to step 3, taking the integral on both sides. So you'll see a few problems like this where you don't actually need to separate anything. As soon as you make the differential, you're ready to integrate. What is the integral of just dy? I can put a 1 here if I want. What's the integral of 1? You just get the variable. And since this is in terms of y, I just get y. Well, that's nice. We'll get to that in just a little bit. Now I got to take the integral of all this other stuff. I get 7 natural log of x minus 3x cubed over 3. Well, the 3's just cancel out, so I'm just left with minus x cubed plus x to the 7th over 7 plus c. Very nice. I integrated both sides. Did I give you an initial value? I did not give you an initial value, so you can't solve for c. So step 4 is unnecessary. What about step 5? My y is already solved for. I don't need step y either. So this is the most simple type of differential equation, and that's because it's just like our antiderivative problems where I just gave you the derivative straight out, and all you have to do is just take the antiderivative to find the actual function. So this one is just as simple as taking the antiderivative, and there's nothing more complicated than that. Let's look at another example. This is one that you saw back in chapter 3. When we talked about exponential functions, we talked about one major property, or one of their major properties, is the fact that their growth rate is proportional to their output value. And we wrote that mathematically like this, right? dn over dt represents the growth rate because it's the derivative, and it's equal to a constant multiple of whatever the output value is, n. Well, guess what? This is a differential equation. And I can solve it in the same way that we can solve it using the separation by parts process. Step 1, write it as a differential. Well, this is nice because you already have the Leibniz notation there, right? dn over dt, so 0.03 n dt. There's my differential. Separate your variables. Well, I don't have a t variable at all, just the dt, but I do have an n, so I need to get that n over to the other side. So I'll go ahead and just divide both sides by n. Do yourself a favor, leave the constant on the t side, just move the n over, and I'm left with 1 over n dn equals 0.03 dt. Okay, step 3, integrate both sides. Okay, well, we've already done this integral on the left side, right? 1 over u du, 1 over n dn. This is just the natural log. Oops. Move back to black. This is the natural log of n. Remember, I'm not going to worry about the plus c on my left side. I'll worry about that on my right side. Integral of 0.03 dt. Well, that's just the integral of a constant, so all I have to do is just slap the variable next to it. Just multiply it by whatever variable I'm integrating by, and I'm integrating by t, so I get 0.03 t. But here's where I'll put the plus c. Now, once again, I didn't give you an initial value, so I can move past step 4. There's no initial value. Don't worry, we will do another problem where you have to solve for the initial value. So I'll go ahead and skip to step 5. Solve for, well, in this case, it's not in terms of y. What's my output variable? My output variable is n. So I'm going to solve for n. How? Remember, to get rid of that natural log, just put everything to the power of e. I'm left with n is equal to e to the 0.03 t. And then I'm going to do that same thing where I'm actually going to split this up into two different exponential functions. And since e to the c is an arbitrary constant, I can just rewrite this as n equals c e to the 0.03 t. And there it is. You'll notice that looks like an exponential equation with my growth rate of 0.03. I just don't know the initial value because I didn't give you the initial value. Okay, let's try one more. Remember, at any point during these videos, you can pause and try out some of the homework problems if they look similar, because all of these examples should look familiar if you're looking through the homework. Let's try this one out. Y prime is equal to 3y to the negative fourth, and let's go ahead and do an initial value for this one. So I'm going to say y of 2 is equal to 5. Okay. Well, let's stick to my steps. Let's write it as a differential. And hopefully we're noticing just how straightforward this first step is. I'm just going to rewrite y prime as dy, and then that dx that's normally on the bottom, I'm putting on the right side. Okay. Next, let's separate my variables. I have a y on the right side with my dx, and I want that y on the left side. Well, remember that y to the negative fourth? I can rewrite that as dy equals, what, 3 over y to the fourth? Negative exponents mean they're in the denominator. Well, that might make it a little bit easier to move. That just means I can multiply both sides by y to the fourth. If I do that, I have now successfully separated my variables. Step 3, integrate both sides. Okay, I will now integrate both of these sides. Integral of 3dx, remember, since that's just a constant, you just multiply it by whatever variable you're integrating by. 3x plus c. Integral of y to the fourth, I get y to the fifth over 5. Very nice. Don't have to worry about a plus c on the y side. Okay, step 4. I do have an initial value, so I'll go ahead and use this now. Remember, you have to choose right now. Am I going to do the initial value now or later? I would recommend now, but don't go solve for y and then come back and do the initial value here. You got to choose one or the other. So let's go ahead and do the initial value now. I'm not going to solve for y yet. I'm going to plug in the initial value first. Okay, what do I plug in for y? There's my output value. So I get 5 to the fifth over 5 equals, what do I plug in for x? That's what this value is. There's my x. There's my y. So we get 3 times 2 plus c. Whew, well, 5 to the fifth divided by 5 is 625. I get equals 6 plus c. What does that mean? C has to be, subtracts both sides by 6, and I get 619. So now what that allows me to do is that allows me to rewrite this equation, with 619 plugged in for C. So go ahead and plug that in for C now before you finish solving for Y. Okay. The reason why I have to put 619 in here, why do I have to put it in for this equation? Because that's where we used my initial value. Whatever step you are at when you use the initial value, that's where you have to plug in the C value. Whatever you solved for C, that's where you got to put it. Okay, so now I can solve for Y. That's my last step. I'm going to multiply both sides by 5. I get y to the fifth is equal to 15x plus 3095. And then I'll take the fifth root. Whatever I do to one side, I have to do the other. And so I end up with the fifth root of 15x plus 3,095. Okay, go ahead and try this out on your own. Let me know if you have any questions. Have a great day, guys.